Have a good student. Today I will discuss about the relationship of line and phase voltage and current in a delta connected circuit. In my previous video I have discussed about the star connected circuit. Okay, so today I will discuss about the relationship of line and phase voltage and currents in a delta connected circuit. Okay, so at first we have discussed about the line and phase voltages. For this, to understand the relationship between the phase voltage and line voltage, consider the figure shown here. Okay? It is clear from the figure that the voltage across terminal R and Y is VRY, which is also V12. So here V12 equals to VRY. Okay. Similarly, V23 equals to VYV and V31 equals to VBR. Okay. Similarly, V23 equals to VYV and V31 equals to VBR, where the phase voltage is V12 equals to V23 equals to V31 equals to V phase. As this is a balanced circuit, so V12, this is phase voltage, V12, this is phase, this is three phase, V12 is phase voltage, V2 is phase voltage, V31 is phase voltage. So V12 equals to V23 equals to V31 equals to V phase. Okay, and the line voltage are, this is phase voltage, this is line voltage are VRY, VYV and VBR. VRY, VYV and VBR, which is line voltage. Hence, in delta connection, prove that V phase equals to V line, because V12 equals to VRY, V2 equals to VYV, V31 equals to VBR, because this is a balanced circuit. So VL equals to V phase. So in delta connection, line voltage equals to phase voltage. Okay. Now the relation between phase current and line current in delta connection. Again we have to draw the peak. This is the peak. We have to draw the phasor diagram also. This is the phasor diagram. Okay. As in the valence system, the three phase current I12, I23 and I31 are equal in magnitude but are displaced from one another by 120 degree angle. The I12, I31, I23, these current are equal in magnitude but are displaced from 120 degree angle. Okay, hence I12 equals to I23 equals to I31 equals to I phase. Okay, if we look the above figure, this figure, it is seen that the current is divided at every junction 1, 2 and 3. There are three junctions 1, 2 and 3. So current is divided at every junction. Look here. Now applying the Kirchhoff law at junction 1. In junction 1, what happened? The incoming current are equals to the outgoing currents. So the I31, this current is I31, is equals to IR plus I12. So I31 equals to IR plus I12. Okay, and their vector difference will be given, which is IR equals to I31 minus I12. The vector I12 is reversed here and is added in the vector I31 to get the vector sum of I31 and I12 as shown in the figure, which is IR. Look here. So the vector sum of I31 and minus I12, I31 and minus I12, and the resultant vector is IR. Okay. Also here the I12 and minus I23 is the vectors, and the resultant vector is IY. Like this, I23 and minus I31, the resultant vector is IB. Okay, so we took the IR. Now from here, IR equals to root over I31 square plus I12 square plus 2I31 I12 cos 60 degree, because these two are phase difference with 60 degree electrical angle. Okay, so here IR equals to line current. This is line current, so we can write IL. So I31 and I12 is phase current. So I square phase plus I square phase plus 2 into I phase into I phase, and cos 6, the value of cos 60 is 0.5. So the total, so from here IR equals to IL. Okay, and IL equals to root over 3 I square phase, which is root 3 I phase. Okay, so similarly we can write IY equals to I12 minus I23, and IV equals to I23 minus I31. So IY, the resultant vector, which is coming from I12 and minus I23, and IV I23 minus I31 IV. Okay, same. From here we can write IL equals to root 3 I phase. From here also you can write IL equals to root 3 I phase. Okay, so hence it is proved that IL equals to root 3 I phase. So in delta connection, the line current equals to root 3 phase current, and the line voltage equals to phase voltage. Okay, so if you have any query, please contact with me, and please like, share and comment and subscribe my channel. Thank you.